In this video, I'm going to show this Serum patch that I made a few years ago and how to make it real quick. And then after that, I'm going to go into some level of detail as to the actual mechanics of the audio and what properties of sound we're using to give this sound the effect that it has. This patch utilizes some properties of Unison in order to create this sort of fake arpeggiator kind of effect. It's really interesting and it can add a lot of depth to simple MIDI sections. For instance, here I'm just going to play some minor ninth chords, and I'll let you hear how that sounds. Sorry for the crackles there in the audio, but hopefully you could hear it all right. And we'll go ahead and get started remaking this patch now. So I'll put in a new instance of Serum, and I'll copy the MIDI over. All right. So for starters, we're going to go ahead and set oscillator A to be a sine wave. And I'm going to use basic shapes wavetable, and it should default to sine wave in the first wavetable position. And now I'm going to go ahead and set Unison up to 5 voices. It's a little easy on the CPU. I don't want to go too high for now while I'm recording, but you could set that however you like. It's actually a really good thing to experiment with later to make the sound a bit more your own. And in addition, I'm going to bring the Unison detune down a bit. Not too much, but down just a little bit. And now I'm also going to set the phase randomization to 0, and I'll push the phase back to 0 degrees. And this is going to do some cool things to the sound. You can also mess with this later if you'd like. It's a good thing that can change the sound quite a bit. And so right now it's going to sound like this. Just sounds like unison sine waves because that's what it is. And the effect that we're going for, that we're going to accentuate, is already there, but we're going to do a lot of stuff that's really going to bring it to the forefront and make the effect much more pronounced. So we're going to go ahead and do some FM, and we're going to enable oscillator B and bring its level all the way down so that it's not coming out through the output, since we just want it as an FM source. And we'll go to basic shapes again, and this time I'm going to put on a square wave, and I'm going to also bring the phase randomization down on the oscillator B here, and I'll push the phase back about to 90 degrees just so we're not right at that vertical. And so now we're going to go ahead and in our warp section here on oscillator A, let's go to FM from B, and we'll push it to about 35%. And I'm going to bring the volume down a bit now, and we'll take a listen to this now. So that really changes the timbre of the sound, and oscillator B is a really good place to start if you want to change the sound for yourself, trying different waveforms and things like that, because that's going to radically change the timbre of the sound. So one thing we're going to do is in the global tab of Serum here, I'm going to bring the unison width down, and this is something I'm going to go into more depth about in the latter part of this video. If I bring it all the way down to 0, the effect becomes really pronounced. Where it sounds like the notes are sort of re-triggering. And you don't have to bring this all the way down to 0 if you don't want to completely eliminate your stereo field. But even if you do, there's ways you can bring it back. For example, later we're going to use a filter, and you can set an LFO on the filter pan, which I'll probably go ahead and do. And that can give you some stereo information going on rather than just having this mono signal. And also you could use something like a dimension expander, which is built into Serum here in the effects tab right here. So I'm not going to bring it all the way to 0 for now. I'll probably leave it at around 20 so that it's not just mono. You can hear how this sounds. So that's actually the main bulk of the sound. In the original example, I also had a filter on. So I like to use the French low pass filter in Serum under the miscellaneous section. So I'll set that on, push the drive up a bit, maybe 25%, and push the cutoff to around 900 hertz, 950. And so that'll roll off some of that high end there. So that's pretty cool. I'm going to put a LFO on the cutoff as well, just a slight modulation, not really too much, maybe around 10%. And this LFO is BPM synced right now. I'm going to push it to bar on the rate. So maybe 2 bars. And that'll open and close the filter and make the sound kind of breathe a bit. And so, yeah, that's really most of the patch. There's a couple little things you can do that I like to do on a lot of my patches that I make because it adds some interesting textures. One of those things is going to be putting an LFO on oscillator B phase. So you're actually going to be sort of creating a sort of Doppler shift kind of effect within oscillator B. And since we're not sending oscillator B out, it's only going to be affecting the modulation that we're doing through FM. So I'll put LFO2 on oscillator B phase position, and let's try about 18-20%. Give that a shot, and we're at quarter note rate on this LFO right now. That's subtle, but that's kind of nice. And one more thing I like to do on a lot of patches is in the matrix section of Serum, you can set Chaos 2 as a modulation source. And this is an oscillator in Serum that just generates kind of a really crazy waveform that you can use to modulate a lot of parameters pseudo randomly, I guess. So I'm going to set Chaos 2 to global master tuning and set this to 1% on the amount. Bidirectional. Bidirectional is important. Otherwise, your whole sound will be shifted out of tune, and this way it'll detune up and down, so your median there is still the same. And I'm going to bring the output amount down to around 10%, maybe 15. I just tweaked the filter cutoff and the FM amount just a little bit there. But yeah, that's the sound. And if you're interested, next up, I'm going to talk about some of the science behind it and how the patch works in terms of audio properties. But otherwise, that's how you make the sound. So now we're going to look into some of the mechanics behind the sound that cause it to behave in the way that it does. And we'll start with talking about Unison in general and how it works on a basic level. Unison creates multiple instances of whatever waveform you have on your oscillator and then distributes those instances across frequencies that surround your root note. So whatever MIDI note you play, Unison will also play waveforms at frequencies that are a little bit higher and a little bit lower than your actual root note. And an important distinction to make about Unison is that it's not a post-processing effect. It's an internal setting of the oscillator that creates, more or less, multiple instances of the oscillator that then flow through the whole signal chain of the synthesizer. And a side effect of this is that using Unison, especially at higher voice counts, can cause really high CPU usage. And Serum patches are pretty notorious for their CPU usage, and this is a pretty big reason why. For instance, if you're going to play a chord that has 5 notes, and you're using 16 voices of Unison on just one oscillator, you'd be using 80 synth voices to play the chord. Serum has a voices counter in the bottom right of the UI that you can use to keep track of how many voices you're using at a time. The difference in frequency across the Unison voices is controlled by the detune knob in the oscillator's Unison section. There's a picture of this section in the bottom left of this slide. It's worth noting that the detune knob is not linear, so if you want to set actual specific percentages, refer to the decimal value that shows up when you adjust the knob. The detune knob sets the detune of the voices as a percentage of the Unison detune range, which is a setting located in the Global Settings tab of Serum. So with a detune range of 2 and a 50% detune set, the voices would be spread by 1 semitone up and down from the root note, given a 2-voice unison. And these different voices that the unison creates and their frequency differences are what we use in this sound to create constructive and destructive phase interference. In many synthesizers, including Serum, the voices of the unison are spread across the stereo field to some degree, and you can adjust how much Serum does this using the unison width control in the global settings. We used this earlier in the video when we were making the patch to amplify the effect, and we'll get more into detail about that later. So here I've constructed a simple example of a 2-voice unison on some graphs. In the graph on the left, we show 2 sine waves emitting from the left side with different frequencies with the same initial phase. The blue sine wave has a frequency of 1 Hz and the red wave has a frequency of 1.2 Hz. You'll see that over time, the red and blue waves sometimes line up and are sometimes nearly opposite. This is the phase conflict that gives us constructive and destructive interference, respectively. On the right, the white wave is the sum of the red and blue wave. So if we played the red and blue wave out of the same output, like on a lot of hardware you'd have mono inputs and outputs, the white wave would be the resulting output waveform. Note that when they constructively interfere, the value of the white wave is at times higher than either of the two input waves, and when they destructively interfere, the white wave has a value less than the input waves or zero. This is a bit of wall of text here, but hopefully it's not too bad. When you set the phase randomization to 0 on the oscillator, it makes all the unison voices start at the same position along the wave, regardless of their frequency. This means that each time you trigger a note, the waves will propagate through time in the same way, and predictably. This also causes a really strong constructive interference right at the start after a note trigger, as both sine waves will increase from 0 and constructively interfere. And generally, you would try to avoid strong conflicts like this in mixing, but in this patch we're doing it on purpose. And as a side note, you can have a whole separate conversation about the implications of pure stereo in mixing, like for instance mixing on headphones versus mixing on speakers, and mono compatibility and things like that. But in this video, we're just focusing on sound design rather than mixing, but maybe that would be something interesting to cover in the future. Now also note that frequency values do not scale linearly across the keyboard. A note that has a frequency value double that of another note is 1 octave higher than the lower note. In a similar fashion, unison detune is not defined in terms of hertz, but rather in terms of notes or frequency ratios. So what this ends up meaning for us is that notes at different frequencies exhibit the amplitude pulsation effect of this sound at different speeds. Higher pitched notes will have the effect happen faster than lower notes. This is because the frequency difference between voices of a higher register note will be larger than the frequency difference between voices of a lower register note at the same detune settings. In addition, because of how unison is an internal setting and not a post effect like how we mentioned earlier, the speed of the effect is independent per note. So this means in a chord, the individual notes of the chord are having the effect happen at different rates. If you go back and listen to the chord we played in the beginning of the video when we were showing off the sound, listen for how the bass notes move slowly and the higher notes pulse faster. So here's a visualization of the frequency spread of unison voices across registers causing that difference in effect speed that we just talked about. And note here that the frequency scale across the x-axis is not linear, and this is common for frequency analyzers, but it makes it look like the difference isn't significant between the note on the left and the note on the right, but quantitatively they are. On the left, we were playing an F-sharp 4 sine wave out of Serum, which has a root value of just about 370 Hz. The unison was set with a detune range of 2 notes at 2 voices and 100% detune. So with those settings, the lower peak is an E4 and the higher peak is a G-sharp 4, and these are the 2 voices of the unison. And using a table of note frequency values that I'll link in the description, we have a frequency difference here between peaks of 85.67 Hz. And on the right, we have the same detune settings applied to an F-sharp 6 sine wave, so 2 octaves higher. And the F-sharp 6 has a root value of about 1.48 kHz. And the voices are again spread by 2 notes off the root because of the unison settings. So the lower voice here is an E6 and the higher voice is a G-sharp 6. And this gives us a difference between voices of 342.71 Hz, which is significantly more than the 85.67 Hz between peaks of the lower register note at the same detune settings. So this is why higher register notes exhibit the amplitude pulsing effect faster than lower notes, as the notes have more significant frequency differences, causing them to fall in and out of phase more quickly. And this effect continues to scale as you work your way up into the higher registers of the keyboard. And this is demonstrated here. On the left, we have the same 2 sine waves as before, with blue having frequency 1 Hz and red 1.2 Hz. On the right, we have 2 sine waves, with blue having frequency 2 Hz and red having frequency 2.4 Hz. The waves within these 2 sets have the same frequency ratio separating them to simulate the frequency spread of a unison. So for both of these plots, the red wave has a frequency that's 1.2 times the frequency of the blue wave. And the sums of the waves are plotted as well in white for both sets. So the white waveform would be our resulting output for both sets of waves. Both x-axis scales here are the same, 8 seconds, and you can see that the output waveform of the higher frequency waves on the right has more overall cycles along the time interval than the sum of the lower frequency waves have. And lastly here, to demonstrate the effect of when we reduce the stereo spread to 0 to amplify the effect when we were making the patch, I've also plotted the amplitude of 2 instances of a sine wave with 5 voices unison at 10% detune and a 2-note unison range. I've shown it here on a frequency analyzer as well as an oscilloscope. On the left is the note with full unison stereo width, and the right is the same note with 0 unison stereo width. At the lower stereo width, the result of the effect is notably different, especially in the average dynamic range of the output signal. On the oscilloscope, The x-axis scale is the same for both plots, and the plot shows that the points of strong constructive interference happen less frequently, with less average amplitude in between. So that's all I have to cover for this sound. Hopefully that was interesting for you. Thanks for watching.